Good morning, everyone. So, today I will be presenting my seminar on the topic subset sum problem, which is an important problem in algorithm analysis. So, it is related to NP complete problems. The meaning is that it is difficult to solve efficiently. So, here I will be covering backtracking, dynamic programming approach, and what is NP complete also. We will be discussing all this. So let's learn what is a subset problem. So the problem is given a set of number and a target value, say a W. We need to check if any subset adds up to the target. So, it is a simple example from this we can understand. That is, there is a set which contains five numbers, that is 5, 6, 10, 11, 16. We can perform uh, 21. We get a target 21 when adding this 3 digit or this 2 digit or this 2 digits. So, we have multiple ways to get this. So, this is a given set of number and we have a target value and we find which all are the subset that add up to the target. So we have two choices, whether we can include it or we can skip it. So every element, there is no necessary to add every element, or there is no necessary to include an element or to skip another element. So this is it creates a possible subset of 2 raised to n combination. So the real world application comes like a budget allocation, task scheduling, and cryptography, that is a knapsack based encryption. So let's learn what is NP hard. That is, we know what is NP hard. There is NP hard, NP complete. So this problem is easy to check but hard to solve. If someone gives you a subset, you can quickly verify it. But finding that subset requires checking many possibilities. So the number of subset grows exponentially, that is 2 raised to n. That is why we call it as NP complete problem. So our disadvantage or the challenge here is the NP hard problem. So this is the brute force time complexity. So we need a smarter method instead of a brute force. That is, first of all, we have approach one, that is backtracking. So the backtracking we all have studied in the beta classes. Sorry. That is backtracking tries all the possible subset using recursion. At each step, we either include or exclude an element. So if a path doesn't work, then we go back, and that is known as backtracking. So we can skip useless path, that is using pruning method. And the time complexity we achieve here is the big of 2 raised to n. And big of n is the space complexity, that is due to the recursion. So these are the steps. So first we start with an element and we have a sum equal to 0. We include the element, reduce the remaining sum and exclude the element, keep the sum unchanged. And then we recurse until we get a sum or we get a dead end. So next we are learning about what is the dynamic programming is that backtracking repeats like the same calculation many times. So the dynamic programming avoids it by storing the result. That is, we use a table where each entry tells us if a sum is possible. We build the solution step by step. That is, here we can see the set and the target, and then we check the true or false for each during the iteration. And we get a time complexity of n into w and the space complexity of n into w, which is much faster for a larger input. So this is what a dynamic programming and this is what is a backtracking. So let's compare both of this. That is, backtracking is somewhat simple, but it is slow for a larger input. And we know it is recursive, it uses depth first search, and dynamic programming is a 2D table that is a bottom up approach. And we know that it is faster and it avoids the repetition, and backtracking is useful when we need the actual subset. And dynamic programming is better when we only need to check if a solution exists or not. So the time complexity is big of 2 raised to n for backtracking and n into w for dynamic programming, and n is the space complexity. Big of n is the space complexity for the backtracking, and n into w for the dynamic programming. And backtracking is, we know that is slow, and dynamic programming is faster. And the small inputs are only allowed in backtracking, and dynamic programming requires larger input. It does not need pruning, but backtracking requires pruning. So, choosing the backtracking for a smaller n when you need an actual subset, and choosing a dynamic programming when n and w are large is a very feasible case. So, when coming to the key takeaways, that is, subset sum is a classic NP complete problem, and the backtracking explores all the possibilities, but it is slow, and the dynamic programming improves the efficiency by storing the result. And the key idea is it optimizes by avoiding the repeated work. So that's it. We discussed about the dynamic programming and we discussed about the backtracking and we discussed what is a subset problem and how to find the subset problem using both of the approaches. So thank you.